Let's consider this pentagon figure. We want to determine how many lines can be drawn between the vertices of this pentagon, and we want to count all possibilities. So what we do, well, first let's draw all the lines, and we can actually count them easily enough. There's 1, 2, okay, and we've drawn all the lines that we can draw from this point. And now we draw all the lines we can from this point. Here's another one, and here's another one. Then we draw all the lines we can from this point. Now we've already got one. Okay, this line here connects these two vertices, but we can draw one down here. And then we can look at this vertex, but we've already drawn both of the possible lines here. We've already drawn both of the possible lines to this vertex. And of course we already had the lines that form the pentagon. Now we see that each vertex, there are 4 lines coming off of each vertex. Okay, 4 lines coming off of this vertex, 4 lines coming off of here. Okay, and we can go around and see that there are 4 lines coming off of each. Now there are 5 vertices around the pendulum, or the pentagon. 5 times 4 is 20. Are there 20 lines here? You might pause and think about that question and ask yourself, why is it that each vertex has 4 lines coming off of it, and there are 5 vertices, but there aren't 20 lines? You can count them. You'll never find 20 lines connecting vertices in this picture. And you might pause and think about that for a second. Assuming you have or have chosen not to, let's just look at what all this means. Well, you see each line connects 2 vertices. So if we count all the lines coming from this vertex and try to count all the lines coming from this vertex, well, this line will have been counted twice, right? Another way of looking at it is, of course, that each line connects 2 vertices, so if we count all the lines coming from each vertex, each line's going to get counted twice, isn't it? So really there are only 10 possibilities. Now we've gone around the figure systematically and checked to make sure that every vertex has a line drawn to every other possible vertex. And we could then count the lines if we had a systematic way of counting them. If we count them as we draw them or mark them off as we draw them, we'll find out that there are 10. Now let's see how we could determine this without actually drawing the figure. What I'm going to do is I'm going to go ahead and label these vertices. I'm going to call this one A, call this one B, call this one C, call this one D, and call this one E. Now we can see that we have a line AB, a line AC, a line AD, a line AE, all coming from A. Then if we go around to B, we have BC, BD, BE. We don't count BA because we already counted AB. If we then go to C, we'll have CD and CE. Again, we won't count CB or CA because we've already counted AC and BC, which are the same lines. Then from D, well, we're only going to count DE because we've already counted this line, and this line. That's nice and systematic. If we then simply list the pairs of vertices in the order we did, well, let's list them and then see what kind of order that is. Okay, we list AB, AC, AD, and AE, and we have all the lines that start at A. Then starting at B and not listing any of the ones that started at A, we have BC, BD, and BE. And then starting at C, we'll have CD and CE. And then starting at D, we'll have DE. And I don't actually think that ellipsis is a good idea there, so I'm going to take my white out and get rid of that. We'll leave this gap here to show that this one is listed starting at a different vertex. Okay? Now, if we list the vertices like this, what have we done? We've listed them in alphabetical order. Having done so, we can be sure that we've got all the possible vertices, because this is all the possible pairs of vertex names in alphabetical order. Now we could list some more pairs. We could list each of these backwards. We could list BA, CA, DA, EA, and so forth, but there's no need to do that. There's another way to list these, and that's using what's called a product table. We could list the vertices again, A, B, C, D, and E, A, B, C, D, and E. Okay, and here we'd have, well, we're not going to list AA, but we'll list AB, AC. Well, let's go ahead and list all possible products. AD, AE, BA, BB, BC, BD, BE, CA, CB, CC, CD, CE, DA, DB, DC, DE, DD, sorry, and DE, EA, EB, EC, ED, and EE. Then we could mark off the ones that don't correspond to unique lines. AA is not a line, neither is BB, CC, DD, or EE, so they're all crossed off. And we've listed AB already, so we're not going to list BA. Similarly, AC through AE would be duplicated here. And similarly, these three would be duplicated here, so we're going to cross them off. These two would be duplicated down here, and this one would be duplicated here. And now we have left the 10 line segments again. Okay?